Hello, we will review wave basics today. So before I start with waves, I'd like to introduce you with the waves all around us. So what is the wave that you can think of right now? Definitely water waves, right? That we see in the rivers and the sea. So they are called water waves. And any other kind of wave? We talk about radio waves a lot. They are electromagnetic waves. So before we can get that specific, let us try to understand what waves basically are. So water waves. Waves are one sort of disturbances, that is, waves are disturbances, or we can also say it's vibration, same thing. So waves are disturbances or vibrations. This vibration can carry energy from one point to another. That is, waves carry energy. Now the beauty of wave is that for the energy to be carried from one place to another, the particles that are vibrating need not move from one place to another place. The particles can just vibrate, from a mean position. So without the movement of the particles, waves can transfer energy. Suppose here we have a point A, and here we have a point, say, that is B. When we are talking through your cell phone, say your home is at A and your friend's home is at B. Now when you guys are talking, the sound energy is being carried through the electromagnetic waves like this. So see, the waves are some sort of vibrations. Something is vibrating there and the energy is getting carried away from A to B. So waves are disturbances or vibration that carries energy without the transfer of the particles. The particles that are vibrating, or whatever there is that is vibrating, do not need to be transferred. Okay? Now, before we can talk further about waves, we must understand how we categorize waves. So as we know that waves are the disturbances, so something must vibrate to produce those waves. The vibrating source creates the disturbance which produces the wave. For example, for sound waves, the source can be a speaker where the diaphragm vibrates, or as we speak, the vocal cords are vibrating, right? You see, we have vocal cords somewhere in our throat, inside our throat. They're like this, they're strings that are vibrating. So the vocal cords are vibrating to produce sounds. What happens is that, say we have a speaker. Don't mind my drawing, it's very poor, I know, but just for the sake of understanding, in the speaker we have a diaphragm that vibrates like this. The diaphragm is vibrating sideways here and there. So sound waves are generated. Now, in case of our voice, it's a sound energy. So as I speak, I have vocal cords. Say these are my vocal cords. They vibrate. They keep vibrating, which produces the sound wave. So whenever we can think of a wave, it has a source that vibrates. Without vibration, we cannot have any wave. Now, the waves can be categorized into two different forms based on the nature of their vibration. So, waves can be called either transverse waves or longitudinal waves. Let us see what they mean actually. Wait, before we can get into transverse and longitudinal waves, let us see a typical wave. How vibrations are associated with waves. Let us review that first. Not review, actually let's try to figure out how it works. Suppose we have a rope fixed at one end, say fixed at one end with a wall, and the other end of the rope is, say, held by someone. So this point, the other end of the rope, is being held by someone. Now say you're holding this rope from one end while the rope is fixed at some other point from the other end. Now say we are moving the rope sideways, that is sideways up and down, I mean vertically. How it's gonna look like, say this is the wall and this is the vibrating rope, right? You see this series of ups and downs are moving along the length of the rope. So the vibration is getting transferred from your side to the other side. The rope is not moving from this point A to this point B. It is the vibration that is getting from A to B. Here, if you focus, the direction of vibration is up and down. So this is the direction of vibration. Now let us try to figure out the direction of the motion of the wave. As you move the rope up and down, the series of maximum and minimum shapes are moving sideways from left to right. So we can say that the direction of motion, or the direction of the progression of the wave, is to and fro in this direction, not backward. Well, they will eventually move backward when they get reflected. Anyways, the direction of motion of the wave is along the horizontal direction, say along the x-axis of the graph, and the direction of vibration of the rope particles is along the y-axis of the graph. we say the direction of propagation, that is the direction of motion of the wave, is perpendicular to the direction of vibration. You see, the direction of the vibration is this way. This was the direction of the propagation, and the direction of the vibration on the other hand is this way. So we can say they are perpendicular to each other, right? So when we have the direction of the wave, that is the direction of the propagation of the wave, perpendicular to the direction of vibration, we say the wave is transverse. So in transverse waves, the direction of motion of the wave, or the direction of propagation of the wave, is perpendicular to the direction of vibration of the particles that are vibrating, or whatever the medium is there that is vibrating. It's pretty simple, right? So this is what we have for transverse waves. So in transverse waves, the direction of vibration of the particles is perpendicular to the direction of propagation. Now we have another type of wave, so we will try to figure that out now. Now let us take a spring, helical spring. This spring can be used to demonstrate both transverse wave and the another type of wave that we'll study shortly, which is called the longitudinal waves. So say this is fixed at one end, and if we try to produce a transverse wave by letting it move from another end which is free, we can do that by this, right? So say the pattern is going to be something like this. So let us draw the path first so that I can follow it to draw the spring. Now the spring is going to be like this, right? So the spring can be used to produce a transverse wave as such. That is, if you held the free end then it would have produced such pattern, provided you have moved your hand up and down. So here too, the direction of vibration is up and down, right? Now what about the direction of motion of the wave? The wave is moving from right to left, from left to right, so it's this way, right? So this is what? This is the direction of propagation. The lines are too thick. Let me sort it out. Okay. Now here the direction of vibration is along this length, and as you can see, the direction of propagation is along this way. So what can you say about this wave? What type of wave will that be now? Definitely transverse wave. Why? Because the angle between the direction of vibration and the direction of motion is 90 degrees here. So this is a transverse wave, right? That is what we have seen just a while back. Now we will be using the same slinky spring to produce a transverse wave, where the vibration and the propagation is parallel, that is along the same direction. What if we can move the slinky spring sideways by holding the two ends with our two hands and trying to compress and then release the springs? How it's gonna look like, the movement? You will get something like this. See, we will get this pattern, which means at some point the turns will be spaced out. This region where the turns are spaced out are called region of rarefaction. And in some region you will see that the turns are closer together. So they are called region of compression. Yes, this is a longitudinal wave. How? Let us figure out the direction of vibration here. As I am moving the spring to and fro, the direction of vibration is along this line, arrow. This is my direction of vibration. Right? To and fro, right and left. Now, these series of alternate region of rarefaction and compression is moving along this direction. So this is the direction of propagation. So as you can see, both the direction of vibration and direction of propagation, that is motion of the wave, is along the same direction, that is they are parallel. In the transverse waves that we have studied previously, these directions were perpendicular, but now they are parallel. So they are called, so this wave, this type of wave where the direction of vibration and the direction of propagation is parallel to each other or are parallel to each other, they are called longitudinal waves. That is, the direction of vibration and the direction of propagation is along the same length. This is the direction of vibration and this is the direction of propagation. So we just saw how we can get both transverse wave and longitudinal wave using a slinky spring. In transverse wave, we had series of maximum point and minimum point. That is, in transverse wave, we had a series of maximum point and minimum point, like this, right? So the maximum points are called crest, and the minimum point is called trough. So we can say that we have a series of alternate crest and trough in a transverse wave, but in a longitudinal wave we had a series of what? Compression and rarefaction, which looked something like this for a spring. The turns are spaced out, and then again they're getting closer together. They're spaced out and they're closer together. So we had a series of rarefaction, and as also we had compression region. The crest corresponds to rarefaction, and the trough corresponds to compression, where the displacement is maximum and minimum respectively. We will be talking about displacement later when we study the wave parameters like amplitude, wavelength and stuffs. So for now we're just going to focus on crest and trough and rarefaction and compression. So I hope you now understand what a transverse wave and a longitudinal wave are. So what we have seen so far is that in longitudinal waves, the direction of vibration of the medium is parallel to the direction of wave propagation. Oh, sorry, I forgot to put a space there between wave propagation. There should be a space here. Sorry about that. Anyways, so sound waves and seismic waves, the waves that are responsible for earthquake, are examples of longitudinal waves. Now, examples of transverse wave includes all the electromagnetic waves. We'll be studying about electromagnetic waves in some other video, but examples of electromagnetic waves are light, radio waves, microwaves, X-ray, gamma ray. All of them are electromagnetic waves, and all of them are transverse waves. That is, all electromagnetic waves are transverse in nature, because in all of them you'll see later that the vibration is perpendicular. That is, the vibration is at right angle to the direction of motion of the wave. Okay, so that is it for this video, and I'd like to inform you that this is the first video that I've ever made of this kind. This is my first attempt. I know there has been several mistakes, or you might see that the organization was not that good. Anyways, it was done just, all of a sudden. I hope I'll improve in the future, and I hope you'll find this video helpful. And this is the first part of wave basics. We will have more videos where we'll go deeper into waves. Till then, take care. Bye bye.